A point P moves in the circle x squared plus y squared equals r squared with constant angular velocity omega. Prove that the foot m of the perpendicular from P onto the x-axis describes a simple harmonic motion about the center of the circle. Okay, so we're moving in this circle x squared plus y squared equals r squared, so a really basic circle, something like this. And I have a point here, P, and the coordinates of this point are r cos theta, r sine theta, because these are the parametric coordinates for a circle, x squared plus y squared equals r squared, right? R is the radius. Okay, so if I drop a perpendicular, as the question said, I get my point M. So M has the coordinates, well, it has the same x coordinate, but the y coordinate is going to be 0. So M is r cos theta, 0. So in other words, x equals r cos theta, and y equals 0. Now I want to show that this describes a simple harmonic motion about the center of the circle. Center of the circle being x equals 0, y equals 0, or the origin. Okay, so let me differentiate x one time, and then I'll have to differentiate it again. But x dot is differentiating with respect to time, so dt, d dt of r cos theta, what's that equal to? Well, that's going to be, by the chain rule, d theta of r cos theta multiplied by d theta on dt. Okay, that's just the chain rule, or implicit differentiation. Now, differentiating this with respect to theta, well, r is a constant, so I just have my r. Now, differentiating cos theta will be minus sine theta. And d theta dt is omega. Okay, so that's what x dot is equal to. Now, what about x double dot? X double dot would be differentiating x dot with respect to time, so I'm differentiating this entire thing with respect to time. So d dt of minus r sine theta multiplied by omega. Now, again, this is going to be d theta of minus r sine theta omega times d theta on dt. Now, we already said that r is constant, obviously because it's the circle, it's the radius of the circle, but we're also told that it has a constant angular velocity omega. So that means that omega is not changing with either theta or time. That means it's constant, so I can take it out of this differential operator here. So if I take out the minus r omega, because all those are constant, I'm left with differentiating sine theta with respect to theta, which is of course cos theta, multiplied by d theta on dt, which is omega. So I have minus omega squared from here, and then I have r cos theta. But what's r cos theta? That's precisely x. That's my x coordinate. So I have minus omega squared x. So x double dot is equal to minus omega squared x. And this is simple harmonic motion. This is simple harmonic motion about the origin. And so I've shown that this point M is going to oscillate in this manner, back and forth between r and negative r, about the origin. And I could do the same thing for the y coordinate of a point moving in circular motion. In fact, let's get another color. Let's get green. And if I had this point, maybe if I called this n, I could also show that n performs simple harmonic motion in this manner, up and down like this. And it would be exactly the same, except here I'd have y equals r sine theta and x is equal to 0. I'd follow pretty much the same steps. And that's a property of circular motion, that the x and y components are performing simple harmonic motion. Okay.